Hello everyone, I am Ananya from the Department of Physics, School of Natural Sciences, Shiv Nadar University from India. First of all, I would like to say thank you to give me the opportunity to present my work in the 4th International Conference on Material Science and Nanotechnology. The title of the present talk is Bulk and Surface Electronic Properties of Stable Beta Phase of Tungsten. The outline of the talks are following. First, I'll start with the introduction. Then I'll briefly describe the background of the present study. Then I'll point out some of the objectives. After that, I'll discuss the result and outcomes. What we can conclude from this we'll also have discussed here. And next, the acknowledgements. Tungsten. Tungsten is a very well-known transition metal element. It is also a heavy element. It is in group 6 in the periodic table. The well-known phase of tungsten is alpha common. It is also called bulk phase of tungsten. It is body center cubic in structure. It has 2 atoms per unit cell. The critical transition temperature in superconductivity of alpha tungsten is around 0.01 Kelvin. Apart from this phase, there is another phase of tungsten that is called beta is also available. It is available in thin films and nanostructures. It is in A15 structure which has 8 atoms per unit cell. The critical transition temperature for this phase is around 3 to 4 Kelvin. The cohesive energies and the lattice parameters for these two phases have been calculated and listed in this table. The experimental determination of lattice parameter and calculated lattice parameters are matches quite well. The beta phase of tungsten is considered to be a potential candidate for spintonic application. It shows a large spin Hall angle, so it is considered a spin orbit torque application purpose, and even it can replace the costly platinum in spintonic devices. However, the phase formation and growth and stability of this phase in thin film is still challenging. In 1954, a new phase of tungsten was discovered by Hagen-Sundberg. It was assumed that time that it is a oxide component of tungsten and it can process only via chemical synthesis. Next, it was considered that it is an allotrope of tungsten, belongs to A15 structure. After that, scientists have started to work on this phase, especially to grow the beta tungsten thin films by using physical vapor deposition techniques like sputtering, electron beam deposition technique, etc. There are several studies have been done on that by the variation of thickness of the film, substrate temperature, working pressure, working power, etc. The common thing is that most of the cases people found the presence of oxygen in thin films of beta. Some of them considered that due to this oxygen, this metastable phase gets stabilized. However, the proper quantification of oxygen in this film has been not done. In 2017, a phase transformation is observed in thin films. In 2016, an enhanced spin orbit torque by oxygen incorporation in tungsten film is noticed. And after that onwards, it was considered a very well-known potential candidate for spintonic application. Based on this background, the questions arises like, what is the role of oxygen to stabilize this metastable phase? What is the concentration of oxygen need to grow a stable beta tungsten film in real practice? What about the electronic structure? To consider a material for spintonic application, or spin orbit torque application, it is very important to study the electronic structure, especially the energy bands. Based on this, the study mainly divided in two parts. First part, where we have tried to get the information about the oxygen induced stabilization, the concentration of oxygen in the beta tungsten film. After that, in the next part, we have studied in detail the electronic structure, the density of state and the energy bands. The calculation details are the following. All the calculations have been performed using Vienna-Ab initio simulation package. We have used PBE form of the generalized gradient approximation for the exchange correlation functional. The Brillouin zone is represented by a 15 cross 15 cross 15 K-point mesh. The band structures were calculated using 100 intersections between two consecutive high symmetry K-points. Both the unit cell alpha and beta have been relaxed. The relaxed unit cell have been again used for further calculation of density of state and energy bands. The optimized lattice parameters of alpha and beta are 3.17 and 5.06 angstrom respectively. Next, supercell of alpha and beta have been considered for doping of oxygen. In BCC, there are two interstitial sites, tetrahedral interstitial site and octahedral interstitial site. The oxygen have been doped in both the sites and relaxed the structure. After relaxation, we found that oxygen is favored TIS site in the BCC structure. Whereas in beta, in A15 structure, there is TIS site, however, there is no exact octahedral interstitial site. So we have doped oxygen in TIS and near about octahedral interstitial site. And in this situation also, after relaxation, oxygen is like to sit on the TIS site. First, the unit cell structure have been relaxed as I stated. So the relaxed unit cell structure of pure beta and one oxygen of beta are here, where tungsten atoms are represented by the green circle and red one is for oxygen atom. After doping one oxygen in the unit cell of beta tungsten, there is a gain in energy of approximately 5 electron volt, and it signifies that oxygen is like to stay in beta phase in the tetrahedral interstitial site. After getting this structure relaxation information, we have further calculated electronic density of state for pure cases as well as oxygen doped cases, and we have increased the oxygen doping one by one in the unit cell. In pure beta case, one can see that Fermi level is lying in one pseudo gap, but with doping of oxygen, there is some change in the density of state profile, and with 2 oxygen, there is a significant change in the density of state profile. We have also considered spin orbit coupling effect in our calculation. In the pure beta case, there is no such significant change after including spin orbit coupling inclusion. However, in oxygen doped cases, there is some change can be noticed. Next, energy bands are calculated for all these cases. As you can see from figure A, there are multiple crossing at the Fermi level, and when we have included spin orbit coupling in the calculation, there is a energy gap. We can see clearly the opening of gap at the crossing points. These crossings are called Dirac crossing, and this crossing and after inclusion of SOC, the opening of gap actually directly related to the spin berry curvature and spin Hall conductivity. So it is now well understood that why this beta phase of tungsten is very potential candidate for spintonic application. However, when oxygen is doped in this unit cell, there is no such crossing is observed. Though one crossing is there at around gamma to A direction, but not exactly at the Fermi level like as in pure beta tungsten case. And also with spin orbit coupling, there is not that much change to be considered. But in real practice, in experimental case, we found that oxygen is present in these thin films of beta tungsten. Therefore, to apply these films for device purpose, we need to calculate with the presence of oxygen only. We have to consider this phase with oxygen, as we already get the information that with oxygen this phase is stabilized. Therefore, we have calculated the energy belts in the same symmetry direction for pure and oxygen doped cases. Interestingly, here we have found that at the Fermi level there is some crossing exist even with doping of one oxygen. However, when we went for one oxygen to two oxygen, these crossings are going to vanish. It tells us that certain concentration of oxygen is required to get this Dirac crossing and for application in spintronics. After that, we have considered supercell of alpha and beta. As I stated earlier, we have checked both the side PIS and YS, and both the cases it is found that PIS is more favorable for oxygen to sit. The binding energy and the solution energy for these two cases have been calculated as listed in this table. We found that clustering of oxygen is also favorable. Next, thin film of beta have been deposited by electron beam deposition technique. The thickness of the film is around 60 nanometer. Then this phase is identified by GIXRD technique, and the distribution of elements like oxygen tungsten have been done through cross-sectional TM EDAX mode, where we have found around 15 to 18% oxygen distribution all over the film except the surface and the substrate region. We have also done X-ray photoelectroscopy measurement of that film and we found the charge state of tungsten. Next, also we have done exact study where we found the tungsten and WO nearest neighbor distance. We have also calculated these parameters from our calculation, and this distance of WW and WO matches quite well with the found exact study. Then we have simulated XRD pattern from certain concentration of oxygen doping supercell, like here around 16% of oxygen doping. As we can see, these are matches quite well. However, there is some shift in the peak that is due to the overestimation of the lattice parameter in the calculation. It gives us the idea that this much concentration, like here around 15 atomic percent oxygen concentration, is giving the beta phase in experimental 60 nanometer thin film. So from that we have an idea that this much of oxygen concentration can give a stable polycrystalline beta tungsten thin film. We have checked other concentration as well. Those concentrations are giving disorder beta phase, not the polycrystalline stable beta phase. Then density of states have been also calculated for pure supercell of alpha beta, and the same as we found in the unit cell, the Fermi level is lying in pseudo. Then we have started doping one oxygen 2 oxygen in the supercell, and corresponding electron density of state have been calculated, and we can see that density of state is little bit increasing at the Fermi level with the doping of oxygen. We have also calculated the total density of state, partial density of state, and the effect of spin orbit coupling in the total density of state when 16 atomic percent oxygen is doped in the beta tungsten supercell. So from the figure, one can see the density of state at the Fermi level is mostly d state lattice state. However, the oxygen contribution is there, that is far from the Fermi level. Next, we have compared the electronic density of state in case of alpha tungsten and oxygen to beta tungsten. As we have already get the information that beta tungsten is stable only with the presence of oxygen. Therefore, the comparison have been made with pure alpha tungsten and oxygen to beta tungsten. Interestingly, one can see an enhanced density of state at the Fermi level in the case of oxygen to beta tungsten. This is very important to understand the higher critical transition temperature in superconductivity in the case of beta tungsten. The Tc is related to the electronic density of state as well as vibrational density of state. Here, the change in electronic density of state is also signifying the change in Tc in these two phases. We have also considered surface effects in our calculation, as some of the studies believe that this is not as a bulk phase of tungsten, it is only from the surface oxygen effect. However, we have checked some of the oxygen doping at the surface, but there is no significant changes in the surface have been noticed, and the experimental result is also not well matches with the surface calculation. However, the bulk one is matches quite well with the experimental results. Therefore, from this study, the formation of beta phase of tungsten is well understood. The role of oxygen in the formation and stabilization of the beta phase of tungsten is recognized. Electronic structure of bulk beta tungsten is established here. The Dirac crossing behavior near the Fermi level in the band structure can be well observed in the pure as well as oxygen to beta tungsten. Interestingly, a higher density of state is found at the Fermi level in oxygen doped beta tungsten, which can tells us the difference between superconducting critical temperature in the two phases. Surface electronic density have been also calculated and checked. I would like to thank Professor Alok Kanchilal from SNU and Professor Vijay Kumar in Center for Informatics SNU for their help in this project. My special thanks to Dr. Alain Cleverisser, France from the TM study. I would like to acknowledge the financial support received from the DST ACRB and Sibnader University. Computational work has been carried out on Megas HPC of SNU is also acknowledged. Thank you all for your kind attention.